G'day chemistry students, in this video we're going to be looking at doing some calculations with the Gibbs free energy equation and using the data that we get out of that calculation to predict whether or not a reaction is spontaneous. Let's get into it. So first off, quick refresher, this was introduced in the previous video, but this is the Gibbs equation. It's a way of calculating the change in Gibbs free energy in a chemical process and shows that it is related to the change in enthalpy of the system as well as the change of entropy in the system. And what we can see is that it is just a part of our formula sheet. So that's something that you can access in future assessments. So there are a couple of ways that we can predict spontaneity. We can actually just use this equation to figure out when reactions may or may not be spontaneous without actually having to do any equation. So this is more of a qualitative version of applying the equation. So in any case where delta G is less than 0, meaning that delta G is negative, what it means is that, as we showed in the energy diagrams in the previous video, that there has been a loss in energy as the reaction has proceeded, meaning that the reaction proceeded spontaneously. In these reactions, they proceed naturally under standard conditions. Keep in mind, though, that spontaneous reactions can still be slow. All this means is that the reaction will just proceed under standard conditions without any further need for energy input. Conversely to that, for any reaction where delta G is positive or greater than 0, the spontaneity of the reaction is considered to be non-spontaneous. And what that means is if you've got standard conditions, standard lab conditions, you'll need to supply external energy continuously for the reaction to occur. Now, if we look at this reaction here, we should be able to figure out how delta G can become positive or negative based on the polarity of delta H and delta S. In other words, is it an exothermic or an endothermic? And will the system increase or decrease in entropy? And you can use this table down the bottom to be able to do that. So spontaneous reactions generally favor exothermic processes and favor processes where entropy has been increased. So what you'll see is that for exothermic reactions that increase entropy, all of those processes will be spontaneous, regardless of what this T value is in the equation. Conversely to that, endothermic processes that decrease entropy will always be non-spontaneous regardless of what the T value is. Things become a little bit interesting when we start looking at, well, what about endothermic reactions that increase entropy or exothermic reactions that decrease in entropy? And essentially, those reactions are going to be completely dependent on T. So for low T's, low temperatures, the entropy value has less weighting because it's not going to be multiplied up as much. And for instances where temperature conditions are high, the entropy value will have a lot more swing in terms of the resultant Gibbs free energy. And so sort of as a result of that, we get different G values depending on what the temperatures are. These are a little bit more gray. You can't sort of necessarily predict the resultant Gibbs free energy with 100% confidence. At that point, it can be really important to do a calculation. So what we're going to start doing is also go through a practice question in a minute to show how you can use this equation to be able to calculate delta G and thus determine whether or not a process is spontaneous or non-spontaneous. So as long as you know delta H, you know T, and you know delta S, you can substitute all of those values in to calculate delta G. Once you know if delta G is positive or negative, you can use the same rules that we just saw in the previous slide to determine whether or not that process will be spontaneous or non-spontaneous. Let's go over and have a look at a worked example together. So in this first question, what we're being asked to do is determine if a reaction, or the reaction below specifically, is spontaneous under standard conditions. And we've been given a set of thermodynamic data. So we're looking at the reaction of calcium hydroxide reacting to form calcium oxide, as well as water as a gas. And we've been given some data to go with that. So we've been given delta H, which is negative 109 kilojoules per mole. We've been given delta S, which is 144 joules per mole. And we've also been given some data about the temperature, even though it doesn't look like it, because we've been given the information that we are working under standard conditions. And what that means is that we are working in conditions that is 25 degrees Celsius. So to be able to answer one of these questions, to try and figure out if the reaction is spontaneous, the first thing that we're going to have to do is calculate delta G. Once we've done that, we should be able to make a judgment on whether or not the process is spontaneous or non-spontaneous. So the first thing that we're going to do is draw up a data column to put all of our information in. So we know that we're working with the equation delta G is equal to delta H minus, and it's T delta S. So with the data that we've got, we know delta H. We also know delta S. At this point, I'm also going to be converting this to kilojoules per mole because we can't use both of these values in the same equation. They need to either both be in kilojoules or both be in joules. So this will be 144 times 10 to the negative 3 kilojoules per mole. And we also have our temperature, which is 25 degrees Celsius. But here's the rub. When we're using a Gibbs free energy equation, T always has to be in degrees Kelvin. So degrees Kelvin will be a different measurement from degrees Celsius, but we can do a simple conversion to be able to go between them. If we do substitute in a value that is in degrees Celsius, we're actually going to end up getting the incorrect answer. So whenever we're doing temperature in Kelvin, it's always equal to our temperature in Celsius plus 273 additional degrees. So in this case, standard conditions of 25 degrees Celsius will always be 298 degrees in Kelvin. So we can use that value as well. So what we're going to be doing next is substituting all of the data that we have. So we're looking for delta G. We know that it is the enthalpy change minus our temperature times our delta S value, so 144 times 10 to the negative 3 kilojoules. So there's our equation. All we've got to do is put all of that into our calculator to then find delta G. And so that is equal to negative 151.9 kilojoules per mole. So at this point, we've calculated delta G. We should be able to look at the sign or the polarity of our delta G at the end and determine that the value is negative. And what we know is that for a negative delta G, we have a spontaneous process. So yeah, negative delta G, spontaneous process, and that's the answer for the first part of the question. We've also been asked to find out what the outcome of the reverse process will be. But if we were to write out our reverse process, so calcium oxide plus water forming calcium hydroxide, we would have to change and reverse some of our thermodynamic data. So that would mean that the enthalpy of that reaction would be 109 kilojoules per mole. as well as delta S would be negative 144 times 10 to the negative 3 kilojoules per mole. I'm just going to make a quick adjustment so that this is in kilojoules per mole as well. And so substituting in that data, we're going to again try and find delta G for the reverse process. That's equal to 109 minus 298 times negative 144 times 10 to the negative 3. So when that goes into the calculator, we end up getting 151.9 kilojoules per mole. Just notice too, when we're reporting these answers, they should probably be reported to 3 significant figures, just like delta S there. Technically, our temperatures, the number of significant figures that they have is a little bit questionable. Usually we would say that standard conditions is usually 25.0 degrees. That's about 3 significant figures of accuracy. I'm happy to treat that as 3 significant figures all the way through. So delta S or your temperature both have 3 significant figures, three figures of accuracy. So really, your answers at the end should be 152 kilojoules per mole, or negative 152, I should say, and 152 kilojoules per mole here. And what we'll notice is that for this equation, we have a positive delta G, which means that this is a non-spontaneous process. And there you have it. We have looked at trying to determine the spontaneity of a reaction using Gibbs free energy. There's your couple of examples there. Thank you very much, everyone. In the next video, we are going to continue working on doing some Gibbs free energy calculations. This time, we're not going to be given delta H and delta S outright. We're going to have to use some literature data, some standard values about entropy and enthalpy for the reaction to then be able to do a Gibbs equation. Essentially, we're working towards the same goal, but the way that we get there is going to look a little bit different. But until then, have a good one.